The reason vector, I put vector in quotation marks, typically it's not, but scalar products, in other words, the dot product is called a scalar product. Why?
Yeah, scalar.
A vector product you would think would produce.
Vector.
And for everything that we're doing in here, it does produce a vector. In reality, it produces what is known as a pseudo-vector, or otherwise known as an axial vector. And I think pseudo is vector is one word, axial vector is two words. Axial vector, I think, is the more current term for it. Pseudo vector, if you happen to run across it, it's the same thing. And the difference between them is reflection. That if I have a mirror here, and I have a vector pointing this way, its reflection would look like that. If I have a vector going this way, its reflection would look like that. But if I do a cross product between these two vectors and a cross product between these two vectors, I'm not going to get mirror reflections of themselves, of itself. And that's why they put in the extra label. It does not, it will look and smell and taste like a vector for everything that we do in this course. If you get into senior or graduate level physics, then it might make a difference. It depends on which branch you go into. All right, so let's talk about cross products. Seems like I touched on them before. I'm pretty sure I probably mentioned them when I mentioned dot products. Did I get into what a cross product was? Did you run across it when you were studying physics over the fall break? Okay. So let's talk about cross products. When I do a dot product, I have some vector A, I have some vector B. I can break A up into components, and let's sort of establish I hat, J hat, just why not? So I got a vector, I can break A up into perpendicular components. So we'll call this A parallel and A perpendicular. So A cross B is A parallel I hat plus A perpendicular J hat cross B, which is just actually, which is B I hat. If I were doing a dot product, I'd multiply the I hat parts together, multiply the J hat parts together. Well, there's no J part over here, so that goes away. In essence, you're multiplying parallel parts. Cross products, you're multiplying perpendicular parts. And part of the clue, if you forget, is that the cross are perpendicular. Not necessarily the way I draw them, but in theory, they are. Those are perpendicular line segments. If I FOIL or distribute, I get A parallel I hat cross B I hat plus A perpendicular J hat cross B I hat. Oh, that's zero. Because I hat and I hat are parallel to each other, cross products, because there's nothing perpendicular there, the cross product is zero. Here we end up with whatever that perpendicular component is, times B, times J hat cross I hat. And so, what is that? I assume in Calc 3 you do this, right? Notation probably might be different, but. So what is J hat cross I hat? Either it's been too long or you just don't want to show off. It's a three-dimensional problem. I got I hat, J hat. We need a K hat for the third dimension, and K hat's coming out at us. As a reminder, if it's coming out towards you, think of an arrow. If an arrow is coming towards you, you see the point. If an arrow goes away from you, you see the feathers. So this would be away or into the board, and this is towards you or out of the board. This right here, because you might be thinking K-hat's a third dimension, it could go out or it could go in. Why did I draw it outwards? This is known as a right-handed coordinate system. And my video on the right-handed coordinate system is the second most popular video that I've done. It seems odd, but it is. It is what it is. When you're doing a cross product, there is the right-hand rule. There are many right-hand rules. This is one of them. Most of the right-hand rules come down to there's a cross product in there somewhere. If I'm doing J cross I, or any two vectors, I put my hand in the direction of the first vector, the J hat. So J hat's pointing upwards, so I put my hand upwards. I got 360 degrees of rotation here, so I need the second part to help me narrow it down. I hat is going this way, so I have my hands up, like upwards in the J hat direction. I want it so that when my fingers bend, they bend towards the second vector. So since I hat's going this way, I put my hand up and I bend like that. Now, if you were double jointed or got some freaky hand stuff, do it like normal people would, or most people would, I should say, not normal people. Because what is a perpendicular person? So, hand up, bend your fingers so they go towards the second vector. The thumb points in the direction of the cross product. So in this case over here, this would be negative K hat. Since I said K hat is coming out, J cross I, J's up, I is this way, thumb points away, perpendicular, into the board. Now we could have done it with A cross B there. Put the hand in the direction of A, curl your fingers so they go towards B, thumb points in the direction of the cross product. So I cross J would be I's first. And this is why it's a right-handed coordinate system. If I put my hands in first direction of the first one, curl towards the second one, thumb points in the direction of the third one if you're using your right hand. A right-handed coordinate system has this set. And so, unless spoken otherwise or unless it's defined strangely, we always assume a right-handed coordinate system. J cross K. K cross I.
J hat.
I cross K.
Negative J hat.
K cross J.
Negative I hat.
And J cross I.
Negative K hat.
Which is what we did over there. Commutative property does not hold. The magnitude's still the same, but the direction flips if you change the order. So when I'm trying to figure it out, you can set up your right-handed coordinate system, go through the right-hand rule there, or this also comes down to if I have I, J, and K in order, assuming I can go around the corner, so I, J, K. If I'm going in that direction right there, my cross product will be positive. J cross K is I cross J is K cross I is J. If I'm going in that direction, it's positive. If I go in this direction, it's negative. J cross I is negative K, I cross K is negative J, K cross J is negative I. Questions here? All right, we'll take a break in just a moment. So if I'm doing R cross F, so overhead view of the door, again, let's establish I hat, J hat. I'm going to apply a force right there. I know the individual torque is R cross F. Well, F would be the force I'm applying. R is a vector from the pivot axis of rotation to where the force is applied. If I want to figure out the direction of it, there's several ways of doing it that all should come out with the same answer. If I'm doing R cross F in order to find the torque, well, R and F, I put them tail to tail. And what would be the direction of R cross F? It's a three-dimensional problem.
K hat.
How'd you get that?
Put your hand. Curl towards F. It's going up.
So the torque would be, that's a right angle. Torque would be R, F, K hat. So method number one, exactly as Benjamin had just done, R cross F. We could have done it also with F is in the negative I hat direction. So that's negative I hat. R is in the positive J hat direction. So I have J hat cross negative I hat. Well, I know that J cross I is negative K, but that extra minus sign flips it around again, so we get K hat. And the other way of doing it, this force is going to cause the door to rotate counterclockwise. Do we get it in direction of angular velocity, the spinning wheel?
Yes.
Okay, we did it. Thumb is my axis here. This force wants to make the door spin around like that. So the angular acceleration is going to be in the K hat direction. And since that's the only thing exerting torque on this, they have to be in the same direction. All right, when we come back, we will combine this with the ladder problem, what's known as the ladder problem. And fun will be had by all. All right, let's take a 5-minute break. All right. As we do with so many other things, let's start with the force diagram. We assume that the person who will become a stick figure at some point is going to be up on the ladder somewhere. Since we don't want to know how far up he is going to go, we'll just label that distance x. All right, what are the forces acting on the ladder?
Gravity. The force due to gravity.
Thank you. All right, assuming uniform distribution, so the force due to gravity acting on the ladder is in the middle. Okay.
There are normal forces from the floor and the wall.
Yes, there are. So which way is it acting at the wall on the ladder?
That way, normal to the wall.
All right, so we'll call this y sub h for horizontal. And down here,
Up, normal from the floor.
y sub v.
Do we have the person's normal force?
Yeah, assuming that he's in equilibrium. So, which way is the normal force acting on him?
Depends.
On,
Is the ladder, are we treating the ladder like a plank, or are we treating the ladder like it has actual rung?
it has actual rungs.
Which it depends what part of the rung he's on. But I guess he'd be on the very top.
Yeah, assume that he's on the top of the rung.
But I guess then straight up.
Yeah. All right, so we got a normal force acting up on him, and then down wherever it happens to be. We'll call this y sub p. And what else is acting on him?
His weight.
Yeah. If he's in equilibrium, then those will be equal to each other. I'm assuming that any movement that he makes is so slow that we cannot differentiate between the normal force and the weight. So he's not bounding up the ladder, which would definitely change the problem. What else?
Friction at the bottom of the ladder.
Going.
Away, because the ladder would be, towards the wall.
All right.
Would there also be friction on the wall, or?
I made it frictionless. It becomes a lot more difficult if we have to deal with both of those frictions. So typically, in a physics textbook, at this point, we ignore that.
Of course, I guess if the ground had enough friction, it wouldn't matter.
Right. And if there's more friction on the wall, then the bottom doesn't need to be as much, but with a set static coefficient, it becomes difficult to know which percentage can we attribute. So, all right. So now, if the ladder's in equilibrium and he's in equilibrium, I know the acceleration is 0, total force is 0. So just based upon what is known as translational equilibrium or linear equilibrium, I have acceleration is equal to 0. But it's also not rotating. In other words, my angular acceleration is 0. Radians per second squared. And this is from rotational equilibrium or angular equilibrium, rotational generally. And this is from linear or translational. So we're going to exploit both of these things. All right, so from that first one right here, Well, I know Newton's second law, total force is mass times acceleration. I got two directions, so basically I've got my total force in the horizontal direction is 0, and the total force in the vertical direction is 0. So I get two equations there. All right, let's do those before we get that to torque. So the horizontal force is equal to 0. What's my equation? Guess let's establish. Our I hat equation.
Would be force due to friction minus the normal force. H.
Okay. Oh, equals 0. My J hat equation?
The normal force V minus weight of the ladder and the normal force of the person.
I'm just gonna go ahead and substitute in weight of the person there.
Equals 0.
All right, let's go ahead and do numbers now. So from this first one, I know that my friction is equal to y sub h, which is equal to mu sub s y sub v. Why is it y sub v and not y sub h here?